sort of jump in and give you a 1 minute warning when you've talked for 5 minutes. So with that, let me ask the first speaker, Diego, to start sharing your screen. And our first talk will be by Diego Montalvo, and he'll tell us about the Lagrangian approach for probing dark matter with gravitational waves. So please take it away.
Good afternoon, everyone. My name is Diego. I'm a physics student from York University, and today I'll talk to you about a research project, a Lagrangian approach for probing dark matter with gravitational waves. First, let me describe to you our objective. We want to be able to compute the gravitational waveform and check for the detectability from LISA for a system that can have many different effects that are difficult to model. To begin in this endeavor, let me first describe what our system is. So we're looking at a case of a heavy central object, like an intermediate mass black hole, which would be a dark matter halo that can have varying density and behavior depending on the different models of matter. All this information about dark matter will be encoded in the mass density profile. Now, suppose that we have a second orbiting object, like a neutron star or a white dwarf, simply revolves around the central black hole and interacts with this matter around. This central dynamical friction, as in the halo would exert a gravitational pull object, is slowing it down and accelerating the in-spiral process, in a similar analogy to friction. Now that we have an idea of what the system is, we'd want to discuss, we want to model. First, we need to account for dark matter friction, which can have different dark matter models describing different properties. Following directly from this, we need to add general relativistic corrections for the orbit trajectories, will allow us to compute our desired gravitational waveform, which encodes all of the information about the dark matter halo. Okay, now that I've described the system that we want to model, it's finally time to talk about how we actually do it. It turns out that we can construct a Lagrangian with purely classical Newtonian elements for the two-body problem which you may all be familiar with. Our interest lies in the resulting equations of motion for each generalized coordinate given by the standard Euler-Lagrange equations, which you can see on the left-hand side, followed by the addition of generalized forces on the right, which the first term has a distribution describing dark matter friction. This is followed by the second term, which represents the addition of general relativistic corrections to the orbits and dark matter densities. One great advantage that comes from this is that it's simple to add more terms describing effects into the Lagrangian equations of motion. As an example, the contributions from accretion onto the secondary object. But let's focus on these two main terms. To see some results, as a general cross-check, we first solved these Lagrangian equations of motion without any dark matter contributions, only considering the addition of relativistic effects into this method. This allowed us to compare our results with the known analytical expression. In this case, I'm referring to the left image, which shows a plot of the major axis A as a function of the eccentricity E. This tells us that the orbital parameters reproduce the correct orbits, and we're able to move forward with this approach. We then need to proceed to calculate the gravitational waveform that would result from an in-spiral from this system. But this would be taking into account the contributions for the dark matter profile. As you can see on figure 2 on the right, we're looking at the gravitational waveforms for a system with and without dark matter. Note that there's a dephasing that occurs due to dark matter contribution. At first, both waves would be almost exactly similar, but as the system evolves, these two curves start to differ, and the difference with the dark matter halo become more apparent, just like in figure 2. We may continue to evolve the system and create a record of what we expect how much time a gravitational wave detector like LISA can record. And this is represented by figure 3, where the differences between our are more apparent with regards to no halo when we look into the frequency space. Now, what we're interested in is that we can compare these profiles above the LISA sensitivity curve, which can hopefully shed some light into the nature of dark matter from looking at gravitational waves produced by its density profile. Okay, so in summary, we can have a few conclusions. We have introduced the Lagrangian approach to model the system, which can be adapted to consider more effects. Gravitational wave patterns were calculated, describing a system with dark matter friction with fully relativistic effects under consideration of LISA sensitivity curves. And future comparisons with detection could provide insights into the nature and behavior of dark matter. You can find more details and the rigorous procedure in our upcoming paper, which should be up in the next couple of weeks. Thank you all for your attention.
Thank you, Diego. We have plenty of time for questions. So you can either raise your hand or put them in the chat. So I see that David had a question, which I'll read out. How dense of a dark matter halo are you considering?
Oh, yes. We're considering a relativistic NFW profile, and this is very near in the vicinity of the black hole. Does have a higher density than the regular NFW. The exact scales depends on the mass of the black hole. So you can think of a regular NFW profile, but with a massive spike in the vicinity of the black hole, which depends on the mass of the black hole itself.
Thanks. So maybe I can ask a question while other people are formulating theirs. Yeah, so I was wondering, you mentioned being able to determine the nature of the dark matter from this method. So could you say a little bit more about how you might do that? Would that be from like the different profiles you might have, whether or not it's like pure cold dark matter or not, or would it be extra friction?
Yes,
or what?
Yes, for sure. Great question. We would be considering cold dark matter. Different models for dark matter predict different density profiles, and as a proof of concept, we're considering just the relativistic NFW profile, but this could be fitted for multiple profiles, as in testing different varieties of models, which yield different density profiles. If they, at least probing this, if high enough density, they should be detectable at least above the LISA sensitivity range, and could provide insight into which of these models fits the best the observed waveform.
Great, thanks. And I see Eric Weiss has a question too. What are those spikes in the curves above the LISA sensitivity curve, and why are they diminished in the dark matter halo situation?
Oh, right. Let me go back. Oh, here. Yes. So the central peak just corresponds to this, just the main frequency of the gravitational waves of the spiral. If you could see at the other peaks, they correspond to relativistic effects. Specifically, for instance, the one on the right. You can see my cursor, perhaps. Okay. They correspond to perihelion precession, and if one's have an spiral, and the closer you get to the black hole, the bigger the forces from dark matter friction, and processes such as precession start to diminish to some degree.
Right on. Thanks, Diego.
Okay, thank you. So I don't see any more questions. So maybe you can take Diego and move on to the next talk. So next up, we're going to have Kai Edmund telling us about glitch mitigation and LISA data analysis. Kai, if you want to share your slides, great. Please take it away.
I was muted. There we go. So hi, everyone. My name's Kai Emond. I'm a research student at UBC, working under Jess MacGyver and Scott Oser on the LISA data challenges, specifically on the Spritz verification binary dataset, which brings up the question, what are verification binaries? So this plot shows the LISA sensitivity curve at different frequencies. And as you can see, LISA's sensitivity, it can detect gravitational waves in about the range of 0.1 millihertz to 1 hertz. And that includes galactic binaries, which are represented by blue dots on this plot. So There are about 30 such galactic binaries that we know of pretty nearby, and we've obtained their properties based off other measurements like electromagnetic emissions from accretion. So we can verify that LISA is working properly because we know exactly what gravitational waves we should be detecting from them when we start looking. So those are verification binaries, which you can see illustrated on this plot with little blue stars. So the data I'm working with was simulated by the LISA Consortium, and it consists of gravitational wave signals from 36 different verification binaries, plus instrumental noise, plus a bunch of low amplitude unresolvable gravitational waves from events in the galaxy, and then plus glitches and gaps based off of models from the LISA Pathfinder mission. And glitches, by the way, are defined as transient non-Gaussian noise whose origins we don't know. So the goal of my project is to go from that full data set with artifacts and noise to accurate parameter estimation, ideally for all 36 binaries, but realistically it's going to be fewer than that because some of them have pretty small amplitudes. So the main issue to solve is that artifacts completely drown out the binaries. In this plot, you can see that there's spikes in the amplitude spectral density from the verification binaries. And then once you add in the artifacts, they just completely disappear. So we need to mitigate that. Gaps are one of the artifacts in the data set, and they're pretty easy to deal with. We just look for holes in the data and then fill them in with zeros. This does cause the spikes from the verification binaries to kind of spread out and blur because these sharp edges of the gaps are causing spectral leakage. So to fix that, we can window the data smoothly in and out by multiplying it with half of a cosine. And that makes the spikes quite a bit sharper and reduces the leakage quite a bit. So glitches, we can remove basically the exact same way as gaps. We just set them to 0 and then window out the surrounding data. But it is quite a bit harder to detect glitches. So for example, that is pretty obviously a glitch, but this is also a glitch. And this kind of looks like a glitch, but that's just random Gaussian noise. So the method I came up with to find glitches uses a combination of the data amplitude and this thing I labeled the quadratic statistic, which is the amplitude squared plus the square of the amplitude's derivative. And these statistics are nice because we can derive expressions for their probability distributions, which you can see on the right, both in regular and whitened data, which means you can choose exactly how much data you're willing to accidentally label as a glitch and then cut out glitches based off of that choice. So it turns out that both methods do incorrectly identify quite a bit of data as glitches, but the intersection of the two is actually much more accurate at detecting glitches and detects a lot less pure noise as glitches. And the different colored lines in this plot are just different LISA channels, by the way. So here's a quick illustration of the results. You can see that the amplitude spectral density basically returns to exactly how it was before the artifacts were added in. I will mention that there are still several hundred very small glitches in the data set that don't get detected with this method, but after a few comparisons, they have almost no impact on the data with how small and transient they are. So we mitigated all the most important ones. So with that mitigated data set, we can move on to parameter estimation. And it turns out that you can actually analytically find the maximum likelihood for 4 of the parameters for any galactic binary source. So we can do a coarse search over the remaining 3 parameters to find maxima. And once we found a few maxima, we can iteratively zoom in on those maxima to find better details and get better parameter estimation. And then finally, once you have a good estimate of what the parameter should be, we can start an MCMC sampler in each maximum to map out the posterior. And just to clarify, these are all corner plots, which is what you get when you take a multi-dimensional distribution and then you project it onto 1 or 2-dimensional surfaces. So for example, all the diagonals are just marginalized histograms of one parameter at a time. And as an example, this frequency, the really diagonal plot near the top is a plot of frequency versus frequency derivative. So you can see they're negatively correlated because they have a negative slope. So anyway, altogether, this procedure seems to work pretty well. Every source that was detected in the artifact-free data set that I was given was also detected in the mitigated glitchy data set, which is nice. And the maximum parameter grid search, maximum likelihood grid search is also effective at narrowing in on the true source parameters for starting the MCMC search, even with the artifacts and windowing. Unfortunately, looking at the posterior distribution more in depth, you can see that there is some bias when you add in the artifacts and windowing, especially in amplitude and initial phase. For example, in amplitude, you can see no matter what you plot it against, it's always significantly lower than the true value. And then initial phase, you can also see that the two distributions are pretty distinct from each other. The plot I'm showing here doesn't actually include the fact that we set sections of the data to 0, which is probably why it's underestimating the amplitude so severely, because we didn't tell it that sections of the data are just 0. So I'm currently working on changing the likelihood function used for the MCMC sampler to include that data windowing, which hopefully will eliminate most of the bias. So yeah, questions?
Thank you, Kai. Do you have any questions? Eric, I see you have raised your hand. Report.
Thanks for the talk. That was really cool. I'm just curious, in the with the gaps in the data, were they really big gaps, or if they were small, did you consider like imputation at all just to see what would happen?
They're reasonably sized. I think some of the larger ones are on the order of a day, and the entire data set is a year. So like relative to the entire data set, they're not huge, but they are pretty big.
Okay.
I didn't consider imputation, like that's adding in extra data points to fill in the gaps, right?
Yeah, you do something like non-negative matrix factorization or something along those lines.
Yeah, I didn't quite consider that because I don't have a huge amount of time. I'm mostly working on this over the summer, but it is something interesting that would be neat to look into.
Okay, cool. Thank you.
Great. Daryl, let's see if you're next. Report.
Yeah, thanks for the great talk, Kai. I have learned everything I know about glitches actually from your team at UBC, but maybe you said this at the beginning of your talk. The glitches you're using in the data challenge, are they from the LISA Pathfinder? Are they somebody's idea of what a glitch might look like for LISA? I mean, how good are the glitches? Because I know they change, every time LIGO updates. So
yeah, so they are modeled based off of the LISA Pathfinder glitches, which a lot of the reason why my detection method is very model agnostic. It's because we don't know if the LISA Pathfinder glitches will be good models for the LISA glitches. So hopefully the method I've developed will work with LISA glitches as well, since it doesn't rely on any specific model. But yeah, they are based off of LISA Pathfinder.
Thanks. We have just a little bit of time, so maybe if there's no one else with their hand raised, I'll ask a question. So maybe just following up on Daryl's question, sort of how different is handling glitches in the data for LISA compared to something like LIGO? Can you just import a lot of the technology and algorithms, or is it sort of completely different because it's a completely different algorithm or instrument?
I'll start off by saying I don't have a huge amount of experience with LIGO, so I can't give like a super specific answer, but LISA data channels are a very different data type than LIGO. They use TDI variables, which are fractional frequency deviation. So it's entirely different units and shapes of glitches than LIGO. It's probably possible that some of the more generic glitch detection methods from LIGO could be imported over to LISA, but also the sampling rate is pretty different as well. So, and a lot of the LIGO glitch detection is based on like designed specifically for LIGO with that sampling rate and with those units. So converting to LISA wouldn't be trivial.
Thank you, and thank you for the nice talk.
Thanks.
So next up, we have Jaden Bardati, who's going to tell us about boost galaxy morphological signatures of massive black hole mergers. So, Jaden, please take it away.
Yeah. So hi everybody. My name is Jaden Bardati. I'm an undergraduate student at Bishop's University, and my research is supervised by John Ron and Daryl Haggard. I'll be talking about how we're looking for morphological signatures of massive black hole mergers in galaxies, and we do this through the analysis of mock images of simulated galaxies, like the one shown here. So actually, as Dr. Ron actually mentioned yesterday, when galaxies merge, it's expected that massive black hole binaries are formed. And these binary systems emit gravitational waves, which are in the same frequency range that should be detectable by LISA or pulsar timing arrays. And after one of these gravitational waves is detected, it'd be really valuable to like locate the host galaxy of the system. The only issue is that in a LISA localization region, there are a lot of galaxies, a lot of potential hosts. And so we require new methods to narrow these down and actually identify the host. So because of the dynamical connection between galaxy mergers and black hole mergers, we suspect that there's morphological differences between galaxies that host black hole mergers and those that don't. So our approach to this is to make mock images using stellar population synthesis and dust radiative transfer on a sample of simulated galaxies that host black hole mergers, and then compare them using morphological parameters against those that don't, the galaxies that a control sample that don't. So to illustrate this relation between galaxy morphology and black hole mergers, here I have a plot of a galaxy from a cosmological simulation being tracked through time as a black hole merger occurs. And so in the upper right corner, we see the time since the black hole merger. And then the red X's show the position of the black holes projected onto our field of view. And so we could see that the galaxy has a disturbed structure before and around the time of the merger, but then later settles down. And so what we're trying to see is whether this is like a statistically significant effect and whether we can use it to distinguish between galaxies hosting black hole mergers and those that don't. So in a bit more detail, to do this, we construct a sample of galaxies from a cosmological simulation that host black hole mergers. And then we create a control sample of galaxies which don't host black hole mergers, these massive black hole mergers, and make sure that it's mass matched and redshift matched to the sample, the merger sample. And then we run this stellar population synthesis on the star particles of both of the samples to obtain SEDs, and these SEDs are propagated through the galaxies using dust radiative transfer. And then we obtain spectra that are then convolved over with certain filter bands that we prescribe, giving us these synthetic images of galaxies in our desired bands. And so with these mock images in hand, we can now measure the morphological parameters of both the merger host sample and the control sample, and then we use linear discriminant analysis to obtain a linear function of the morphological parameters that maximally discriminate between the merger sample, the sample black hole merger hosts and the control of regular non-host galaxies. So here are some of the color composite images that we've created using the convolved images from the stellar population synthesis and dust radiative transfer. And since there was already a talk on Castor, I figured the proposed telescope, I figured it was worth mentioning that two of the three filters that are used in these RGB images are matched to Castor. One is in the UV and one's in the optical. And then the third filter is in the IR matched to the Roman telescope. So we use this large range of wavelengths to see which bands would be best suited for this host galaxy follow-up. And then we also match angular resolution and convolve with a PSF. So here is a plot, like a plot of an example galaxy that I'm performing the measurement of morphological parameters. We measure various morphological parameters, including the Searsic index, concentration, asymmetry, and smoothness. Both parametric and non-parametric parameters are included. And then finally, we perform linear discriminant analysis on the parameters which are on specifically the parameters that are statistically significant to maximally discriminate between the sample of galaxies that host these massive black hole mergers and those that don't. And from this, we get a linear function of the morphological parameters that returns a value larger than 0 if it determines the galaxy to be a galaxy hosting a massive black hole merger, and then a value less than 0 if it determines it to be not hosting a massive black hole merger. And the histogram here shows the results of the LDA predictor on some preliminary data. And next to it is the corresponding confusion matrix, where we can see we have about 70% accuracy. It's important to note right now with this plot especially, that at the moment we're aware of several issues with this data, the preliminary data, that we're going to fix, and when fixed are likely to increase the accuracy. For example, we'll be increasing the spatial resolution and the sample size as well. So thank you for your attention.
Thank you. So do we have any questions? So maybe while we're thinking about that, I can ask one. So I was wondering, just based on the simulations and this kind of mock data, like if you had feelings for sort of the intuition behind like what the basic difference in shape is between a galaxy that just, I presume it means just recently merged or merged sufficiently recently in the past to have the two black holes come together or something. What's like the basic shape difference between that and a galaxy that doesn't use the merger?
Right. So typically, I mean, this is something that we'll hopefully confirm with. I'll just go back to this slide. So something we'll hopefully confirm with the statistical techniques. But typically, by eye, it seems to we have this like so if you look at the last plot here, it's sort of the galaxy shape is more defined. Like we have a very clear circle sort of shape, whereas earlier on it's more disturbed because of the galaxy merger that has likely to occur before. So typically you get this disturbed morphology. But in terms of like how we actually measure this, when we go to get a parameter, one of the parameters that measures this is how is the relation between the Gini index and the M20, which are sort of measures of total concentration and measures of concentration to the center. So sort of without going into too much detail, because I realize I'm rambling, if you have near the center of the galaxy, if it's more concentrated, it tends to be that the galaxy is actually more likely to be, it's more likely to have been in a merger, not been in a merger. Whereas if it's more concentrated towards the edges, it's not. And that's because of these dual centers and so on.
Great, thank you. And thanks for the very nice talk.
Thank you.
So next up, we have Vasil Todorov, who's going to tell us about quantum gravity effects and primordial gravity waves. So Vasil, please take it away.
Sorry. Hello, everyone. I'm Vasil Todorov. I'm a research assistant at University of Lethbridge, and this work was developed under the supervision of Dr. Sarya Das and in the collaboration of Dr. Subramaniam from the Institute of Technology, Bombay, Indian Institute of Technology, Bombay. We started with a model of quantum gravity phenomenology called generalized uncertainty principle, which models an existence of an additional scale in the universe. We worked to take it to a relativistic framework to make it a Lorentz invariant additional scale in the universe, from where we took it in the natural progression of constructing a field theory with this additional scale. And finally, in this field theory, we found a spin 2 particle, which obeys an action, which is given to us by quadratic gravity. The particular variation is the one proposed by Stelle. So this is our baseline. So from here, we started to apply this to cosmology. First problem that we ran into is that for stellar gravity, the spherically symmetric solutions are isolated. So that throws the whole perturbation theory out of the question. Luckily for us, using the Gauss-Bonnet theorem, we were able to connect it to another action that describes the same dynamics, which is f of r with linear combination with the Weyl squared term, which is interesting because we can do actual perturbation theory and cosmology with it. We performed a quantization of the action where the scalar terms were quantized using the well-known inflaton procedure, and the tensor terms were the tensor modes were quantized using a fairly novel Fay-Kohn procedure. From there, we were able to find the amplitude of the power spectrum for both tensor and scalar mode, and extract from comparison to experiment, and extract a value for where do we expect to see the first signatures of this additional Lorentz scale. The other observables, namely the spectral tilts and the scalar tensor ratio, does not explicitly depend on our additional scale gamma. However, you can see the tensor mode suppression that we observe compared to the Starobinsky model of inflation. So the tensor modes are suppressed by the addition of this additional scale, which actually comes to us from quantum gravity framework. So quantum gravity suppresses the tensor modes. From there, we decided to do a little bit more classical approach to the quantization of a perturbed FRW background, with a little help from the Ostrogradsky method, because we have higher derivative theories. We were able to extract a quantum gravity modified power spectrum, the primordial gravitational waves. And we, from the power spectrum, obtained projected value of the characteristic strain of the primordial gravitational waves, and compared it to some of the future experiment, including ELISA. Sadly, we can see that our characteristic strain is well beyond below the ELISA detection threshold. We might be able to have some possible detection depending on the scale of the gravitational wave, depending on the scale of the additional scale. And however, there's a silver lining. This is one source, but we have an action that is applicable to many sources. So from here on out, we can apply this to we can apply this framework that we've come up with to any source that we'd like, including black hole merger, including neutron star merger, and everywhere that there are gravitational waves that we can detect. And we'll see different effects. So to conclude, we have now values for the additional length scale that quantum gravity predicts. We have proved that there are quantum gravitational signature in the present day power spectrum of primordial gravitational waves. And we have strong reasons to believe that there will be quantum gravitational effects present in many other sources. Finally, if our gravitational wave spectrum of the primordial gravitational waves actually contains information of how much the universe expanded during the inflationary period. So depending on what we detect, we can draw conclusions if the universe underwent a process of inflation and how much did it expand. And that is all for my talk. Thank you for your attention.
Thank you. So do you have any questions? Maybe I can ask a quick one. So for this sort of minimum length scale that you're introducing, so are we thinking about that as something very small, like the Planck scale, or could it be much larger?
I should have mentioned in the beginning. So this is comparing like the minimum length scale is expressed in terms of the Planck scale or Planck length. So it's when we find gamma 0, that is so that is that many times the Planck length is the scale at which we expect the first quantum gravity effects to be present and like in our data. They're still like quite low in amplitude compared to the leading order, but they will be present. We expect them to be present at this scale.
And could you say a little bit more about what potential effects you might think this theory would have on other sources, you said, like on binary merger gravitational wave signals or things like that, or that's still something you're trying to figure out?
This is something that we are trying to figure out. This is we have a bunch of like conjectures and places to search. The main one is this modification of the actual equation of motion. From here we can simulate quantum gravity effects in the actual ring down signal and try to run that signal against observations to further put bounds on the additional scale that we propose.
Great. Thank you for the answer and for the nice talk.
Yeah, and I'll answer the questions in the chat. Thank you.
So next up, we have Sam Gagnon-Hartman, who's going to tell us about unbiased multi-messenger inference of the Hubble rate. So Sam, whenever you're ready, please.
Yep, sure. Let me just get the screen share set up. Does this look good to everyone?
Looks great. Thanks.
Okay, perfect. All right, so I'll be talking about the subject of my master's research, which is unbiasing multi-messenger inference of the Hubble constant. I will say that my master's project focused on binary neutron star mergers, but similar biases will appear in things like binary supermassive black hole mergers, which are detectable by LISA. So these biases will persist in other object classes. So let's just keep that in mind as I go forward and talk a lot about neutron stars, which are not relevant to LISA. Let's dive right in. So I won't really motivate the existence of the Hubble tension, just say that I think probably everyone's heard of this too many times, that in the past like 10-ish years, we've got sort of two competing measures of the Hubble constant, and the significance of the difference in these measures is pretty high and hard to commensurate. So people are interested in a different measure of the Hubble constant, right? And a really promising one is using standard sirens, or so gravitational wave cosmology. And I'll just go ahead and tell you how that works. The idea with standard siren cosmology is that you've got some object which just telegraphs you two pieces of information. It'll give you its redshift information out of its EM emission, as well as its distance information out of the gravitational wave emission. And so we can detect gravitational waves with detectors like Ligo or LISA or the Einstein telescope in 1,000 years. And then you can detect its redshift from the EM emission using just regular old telescopes. So once again, this research focuses on binary neutron star mergers, since they do produce both EM and GW emission properly. And so we can measure that and call it a standard Siren and get ourselves a measure of the Hubble constant. And so the EM emission component of a BNS merger is called a kilonova, and I'll probably be using that term going forward to refer to the binary neutron star merger sort of equivalently. Now, as for how this relates to LISA, so what's a dark Siren, for example, there is this idea that you could have two black holes crash into each other, and they produce a gravitational wave, which is measurable. But the localization is uncertain, right? We can't just point directly to one galaxy in most cases and say, for sure, these black holes were in that one galaxy. It's more like a general region of space where we're like, okay, it's somewhere in that area of the sky. We have some limit on how far it is in the bottom right from the gravitational wave measurement. And you can create like an ensemble of possible host galaxies and sort of create a dark Siren measurement that way. So it is still possible to do multi-messenger inference of the Hubble constant using these sorts of dark Sirens. And there was a paper very recently about, I think it was called spectral Sirens, to look at if H0 evolves throughout cosmic time. I won't talk about that, but let's just keep that going forward. The bias, so where this comes from. So imagine we just have a bunch of events, say your binary neutron star mergers at different distances, at different recessional velocities. And so this is maybe the distribution of what really occurred in the universe. But it suffers from some selection effects, which cause us to preferentially miss events that are more distant and beneath the mean of this line. If we're to fit just a standard, Hubble's law approximation, okay, how fast is the universe expanding? What you would fit is going to have some bias encoded in it. And this is, in fact, what happens. So there are two sources of bias in these sources. Once again, for BNS mergers, what's really important is the kilonova anisotropy, which is just to say that the EM emission of a BNS merger is anisotropic. It's brighter at the poles and dimmer along the equatorial region. So if you think about all the neutrons being disrupted, all that neutron-rich matter coming out of this sort of explosion, the neutron density is much higher around the equator. So you have it's much more opaque to the radiation that ends up being dimmer. The takeaway there is that we're much more likely to see a BNS merger face on, see the EM component face on anyway, than we are to see it edge on. And when you have an event which is at an oblique angle and you miss it, there is this uncertainty as to whether you missed it because it is at an oblique angle or if it's just too far away, we didn't see it, right? And that is the source of this bias which arises. So our correction scheme for this is just a simple simulation-based inference scheme where we have an event simulator where you're going to simulate multiple events in a suite. So assume we have 8 binary neutron star mergers that were detected, some in EM and some only in gravitational waves. So if you want to look at this little picture, maybe the green ones were standard Sirens and the red ones, we only saw the gravitational waves. From the gravitational wave measurement, you get some information. You get some estimates on the masses, the inclination angle, and the distance. We can draw from that, treating that as a prior, and just re-simulate these events over and over again, using a light curve kilonova simulator to get the emission out of there. Compare the observables to real data and sort of characterize that distance using some metric, which I've called S in this study. And you just repeat that over and over again. This is fed into the second stage, which is the posterior inference stage of the bias correction scheme, where we use a neural ratio estimator to sort of infer a posterior for H0 based on those summary statistics. Now, the reason this can correct for this sort of angle degeneracy bias is because we repeatedly simulate over various inclination angle distance pairs. and then rule out which ones are not consistent with the value of H naught implied by the standard sirens. So we're using these GW only events to sort of import new information, which allows us to correct for the bias in the standard sirens. Neural ratio
Sorry, just,
estimation.
jump in with a warning. We're into the question time. Thanks.
Oh, we are. Okay. Cool. So I'll just skip ahead to the posterior and just take any questions that people might have about any of this.
Okay, thanks. So are there any questions? Right, I mean, maybe you just want to tell us the sort of the punchline that we should take away.
Sure, yeah. Basically, the point of this is that the biases are correctable. Like there's enough information within the events themselves. It's a matter of just getting them to be consistent with each other and exploring the parameter space in a smart way. And you can correct for the bias by just exploiting the information in the non-standard sirens. Similar methods can be used for supermassive black holes, for sure, using like dark sirens, which will suffer from their own biases, right? Like galaxy catalog incompleteness biases. And then of course, gravitational waves have their own inclination angle distance degeneracy, which can be corrected for. But yeah, that's just the takeaway. It is correctable. There's some method that we've concocted for this and will be on the archive within a couple of months.
Great, thank you. Let me check. Are there any more questions? If not, thanks, Sam. We can move on to the next talk, which is going to be given by Jinpan, and he's going to be telling us about mass gap, extreme mass ratio in spirals. So, Jin, whenever you're ready, please take it away.
Okay, can you see it now?
Yep, perfect. Thanks.
Okay, hello everyone. I'm Zheng Pan, a postdoc at Perimeter Institute. Today I will talk about mass gap MRAs based on our recent work. Okay, when we say MRA, we usually mean a massive black hole plus a inspiral stellar mass black hole. And we know there is a special class of low mass black hole called mass gap object with their mass between 3 and 5 solar mass. And we haven't seen them from the X-ray binaries from our own galaxies. But we have seen some evidence of their existence from Ligo events. And in this talk, in this work, we define a mass gap MRA to be a massive black hole plus inspirally mass gap object. And in this talk, we will focus on their formation and the detection perspective. As Juan mentioned yesterday, there are two main formation channels for MRAs. The first one is called the dry MRA formation channel. You see this cartoon plot, massive black hole in the center and a stellar cluster around it. As a stellar mass black hole orbiting around the massive black hole, it will be scattered by the stars and the other black holes randomly. So in some case, the stellar mass black hole can be scattered to a very low angular momentum orbit. In that case, we will find the gravitational time scale for this stellar mass black hole will be shorter than the relaxation time scale. And we will see the stellar mass black hole is captured by the massive black hole and call it MRA formation. In the dry MRA formation channel, there is an important effect called mass segregation effect. This effect tells us that for the different components in the stellar cluster. The heavier component, in our case, it's a stellar massive black holes, are easier to accumulate around this massive black hole. And the lighter component, in our case, for example, the mass gap object, are usually expelled further away. Okay, as a result, the stellar massive black holes are easier to be captured by the massive black hole because they are closer. So the stellar massive black hole will be easier to form memories than the mass gap object. So how easier and how hard? Let's see one example. We consider a Forduschi model with a CGA star-like massive black hole in the center and a nuclear stellar cluster around it with normal stars, mass gap objects, and stellar mass black holes in the cluster. So for simplicity, we assume all mass gap objects are of 3 solar mass, or stellar mass black holes are of 10 solar mass. Initially, we assume the number of the mass gap objects and the number of stellar mass black holes are the same. So we can evolve the nuclear cluster system and calculate their memory formation rate for both stellar mass black holes and the mass gap object. This plot, the x-axis is the time in unit of gigayear. The two solid lines are the memory formation rates for the stellar mass black holes and the mass gap object. You see the orange line is the memory formation rate for stellar mass black holes, and the blue line is a rate for mass gap object. Though their numbers are the same, but we can see the rate are different by 100 or about 100. So that's a result of the mass segregation effect. So the takeaway message is in the dry channel, the mass gap memory formation rate is strongly surprised by the mass segregation effect. Let's say the wet channel. So the picture is similar to the dry channel, except the massive black hole is accreting. So we have our accretion disk there. Now, as a stellar mass black hole orbiting around this massive black hole, and it will first capture to the accretion disk, then migrate inward along the accretion disk. So if the capture time scale and the migration time scale are shorter than the disk lifetime, then it will have enough time for the stellar massive black hole to migrate to the vicinity of the massive black hole and form an memory. Okay. For example, for such a star-like massive black hole with 0.1 times ideal accretion rate, the capture time scale is usually very short, 10 to 100 years. The migration time scale is much longer, but it's usually shorter than the disk lifetime. So let's say.
So sorry, just jumping in with the 1 minute warning.
Oh, okay. So see this plot, the x-axis is the time, y-axis, the two solid lines is the wet memory formation rates for the mass gap objects and the stellar mass black holes. We see in the equilibrium state, the two rates are different by a factor of their mass ratio. In our case, about factor of 3. So if you still remember that in the dry channel, the difference is about 100, factor 100. Okay, so the conclusion is the wet formation channel will be very efficient. For the normal stellar mass black hole memories, the wet channel will contribute an important fraction of them. For the mass gap memories, the wet channel will contribute a dominant fraction. So, and we can use the detection MRI detection numbers of the two kinds of MRIs to infer their number fractions in the stellar cluster. And from that ratio, we can infer the existence of the mass gap and the supernova explosion mechanisms. Thank you.
Thank you, Jen. So do we have any questions? Maybe I can ask a quick one. When we detect an MRI, is it going to be obvious whether or not it comes from a dry or a wet system, just by, I guess, electromagnetic observations or some other way?
Okay, so there are two ways. First, in the dry channel, the MRI orbit eccentricity is usually very high, and in the wet channel, the orbital eccentricity is usually 0. And that's our first way to tell the difference. The second way is the accretion disk may introduce some measurable phase shift. If we can measure that phase shift, we know it comes from the interaction with the accretion disk. So we can distinguish the two.
Great. Thank you, Jen, and thanks for the nice talk. Okay. So next up, we have our final speaker of the session. It's Nair Raza, who's going to be telling us about machine learning and LISA alerts. So whenever you're ready, please take it away.
Can you see my screen and everything's good?
Looks great.
Okay,
Thanks.
perfect. All right. Yeah, so hello everyone. My name is Nair Raza, and I am a graduate student at McGill University at McGill Space Institute, working with Daryl Haggard. And today I'm just going to give a very brief lightning overview of how I've used machine learning to look at classifications of gravitational wave events and how that might be applicable for LISA. And so, of course, no talk about LIGO alerts and multimessenger follow-up can be without mentioning GW170817, the first and only event that we have detected in gravitational waves and electromagnetic counterpart. And that's to emphasize the wealth of information that we've learned from just this one event, and how much the synergy of both gravitational wave events and electromagnetic follow-ups can tell you about the astrophysical processes that are going on. And as has been elaborated, in many talks today and yesterday, LISA has a wealth of sources that will also have electromagnetic counterparts, like stellar compact binaries, so white dwarfs, or neutron stars like LIGO, but these in the galaxy and much before merger, or massive black hole binaries, or extreme mesh ratio in spirals. And so you want to follow up these events with electromagnetic follow-up. And so what does that look like initially? Well, the LVK since 2003 has been producing these public alerts for candidate gravitational wave event detections. And so based on that, you want to know, okay, is this candidate worth following up? Is it actually a real event, or is it a glitch? And so the numbers are, out of the 77 open public alerts that LIGO Virgo had in 2003, 32 were actually glitches. So it's a significant number that's actually, if you follow it up, you later find out that it wasn't a real event. And so if you also want to know that if it is a real event, you want to follow it up quickly. It's time sensitive. You want to get the afterglow of if it's a binary neutron star merger as quickly as possible. So you need a tool that's fast and helps classify what you're looking at. And so that's where this machine learning classifier GW Skynet comes in, which uses data from the LIGO Virgo public alerts to try to classify what kind of event is this. And this is work that was initially spearheaded by Miriam Cavero at UBC, who developed a binary classifier that that decides whether it's, the event is astrophysical or is it just noise? Is it an instrumental glitch? And then work by Thomas Abbott and Eitan Bufaz at McGill developed the sort of next generation, which is this multi-class classifier that you see over here, that takes this data and then in this hierarchical fashion tries to determine, okay, is it a glitch or not? If it's real, does it have a neutron star? Is it worth following it up? Might we expect a electromagnetic signal? And so with this classifier, we were able to predict of those 77, 64 of them were correctly classified as glitches or having a neutron star or being binary black holes. And so the idea is, since this is a LISA talk, could we do the same thing for LISA? So, I mean, this is sort of a schematic showing what the procedure for LISA data looks like. And so there's a few processes involved, as is with Ligo and Virgo. There's multiple steps where you have raw data and some sort of pre-processing, low latency processing. But the idea here is that you also have preliminary event notices and event notices going out to the EM community for follow-up. In this case, this is with the astronomer's telegram. But we can expect, similar data products or some of the same data products that we currently get from LIGO Virgo. So something like the sky localization maps or a measure for the distance or what was the state of the detectors. And so we could ask, could a GBlue Skynet classifier be trained on these LISA alerts, which also, by the way, have glitches, Kai just talked about, LISA Pathfinder saw glitches, and there might be the possibility of glitches in actual LISA data as well. And so, so this is work that is, I guess, in front of me, not behind me, but towards building this machine learning classifier for LISA alerts could involve, as its first step, looking at the simulated events in the time series data that we have in the LISA data challenges, as well as Pathfinder glitches that we have, and try to use those to make mock public alerts and try to train on that. But there's also some differences and challenges that we don't encounter in LIGO Virgo alerts that we might see in LISA, which is that there's many, many more types of real events that we expect to see in LISA. And more importantly, they occur on very vastly varying timescales. You have, signals that are persistent over months, and you have, unmodeled transients that happen in near real time. And that might also mean that if you have a persistent source, that might produce evolving alerts as the SNR accumulates. So this is sort of schematic for a massive binary black hole that's showing, as the SNR accumulates, how the sky localization gets better and better and better. And so these are the main challenges that we might expect to see. And so just to summarize and leave you with that, we have seen with LIGO Virgo public alerts that GW Skynet is a machine learning classifier that works and that can help astronomers make follow-up decisions about whether or not a gravitational wave candidate event is worth following up. Is it real? Does it have a neutron star? And there's potential to transfer some of this knowledge and train a similar tool for future LISA alerts. But as with any next generation facility, that poses its own unique challenges that require careful consideration. And thank you for listening.
Great, thank you for that nice talk. So, have any speakers at hand, maybe? Yeah, Kyle, please go ahead. Eric, I see you have your hand raised.
Thanks for the talk there. This is really cool stuff. I'm sorry if I missed something, but so is it just the 77 events that you trained on?
No. So the classifier is trained on simulated data for binary black holes, binary neutron star mergers, neutron star black hole mergers. And then there's a collection of glitches that's from real data that's collected over the last 3 observing runs.
I see. Is there any like regularization involved in the algorithm?
As far as I'm aware, no.
Okay.
So
Cool.
So like I said, yeah, the algorithm was built over the last 2 years by people before me. I'm working more towards understanding how it's working and how it might be applied for I guess future missions.
Okay, I see. Thank you.
All right, any quick last questions? If not, that brings us to the end of this